And so the goal is to not over allocate frames to processes that we may end up not needing, and then we're gonna end up with a full physical memory. So we don't want that. Instead, we want to modify the page fault service process that we've introduced before to incorporate page replacement algorithm. Okay. So which algorithm, we're gonna learn about them next. But before that, we want to define another bit that is called the modify bit or the dirty bit. So this this will be added to the page table, right? Our page table will actually be looking like that. So we're gonna have the frame number. So the index will be actually the page number that we're looking for. So for instance, index 0, 1, 2, and so on. And then the corresponding frame that this page is allocated to, for instance, frame 11, frame 200, and so on. And then we add the valid invalid bit. So set to 1 or to 0 when it's not memory resident. In addition, we add the modify bit, right? So to represent, if it's set to 1, this means that this page has been modified since it has been loaded from the backend store, right? If it's 0, this means that we did not actually modify anything to this page, okay, since we last loaded it from the backend store. So it's not dirty, it's not modified, okay? Why do we need this bit? Because when we're gonna apply page replacement, so what are we gonna do with the victim, the page that we will replace? To reduce the latency, we're thinking about one path to reduce that latency, which is we are only going to write that victim page back to disk if it has been modified, which makes sense, right? If the version on memory, it's exactly the same as the one on the backend store, which means it's not dirty, it hasn't been modified, then there is no need to write it back to disk because it's the same version. Only when it actually has been modified and the version on memory is different than the version in the disk, then we write it back to the store. And so we're trying to reduce this write-in to disk process because, as we said, it takes time, right? Write-in to disk is slow, and so this will slow the entire process and page replacement down. And so we only do that when it's necessary, okay? When the page is already modified. Okay, so now how can we do page replacement? There are many algorithms that we will discover today. Right, so this figure shows the concept that we just talked about visually. So we said the dirty bit, we only write a victim page back to disk if it's already dirty or has been modified. And so if we define P as the present bit, which means it's memory resident, and M as the modify bit, right? So a page must be written back to disk when? So we said we write a page back to disk only when it's dirty, when it's modified, right? So only in this case we do write it back to disk. Question number 2. Immediately after a page replacement, the bits in the page table of the new page are, so the new page, which means the newly loaded one, will be which one of these? So since we've just loaded it into memory, then we do have to set its present bit to 1. And then since it's still new, we didn't get a chance to change it yet, then its modified bit, it's still 0 as an initial state. So page fault is triggered when? So we do have a page fault when a page is not memory resident. So when P is equal to 0, it's not present in memory. And so before we talk about the replacement algorithms themselves, we want to talk about how to evaluate them or how to compare them. And so we can actually run them on a particular string of memory references that we call a reference string. Okay, so we will compute the number of page faults that this algorithm results in if in case of this particular reference string. So reference string is actually the page numbers, not the full addresses, right? So the page numbers that a process is trying to access or it has accessed. Okay, so we will run our replacement algorithm on that reference string, and we will count how many page faults that algorithm did generate. Okay, so one rule that we're going to follow is that repeated immediate access to the same page number will not actually be counted as a page fault. So if in the reference string we have page number 2 and then immediately followed by page number 2, we're not going to consider this as a page fault, okay, because it was immediately referenced. Okay, so if it has been already replaced here, then that page is already in memory, so automatically there won't be a page fault immediately after that. Okay, and so to understand the concept of a reference string, then this is an example of how to generate a reference string from the addresses that a process is trying to access. So if we assume that the page size is 100 words, right, that means that the first from 0 to 99 is page 0, and then from 99 to 199 is page 1, and so on, right? And so this means the corresponding reference string will be, so 10 will fall in page 0, 11 will fall in page 02, 104, right, so it falls in page 1, 170 also in page 1, 73 still in page 0, 309 is in page 3, 185 still in page 1, 245 is in page 2, 246 in page 2, 434 page 4, 458 page 4, 363 again in page 3, right? So this is the corresponding reference string for these addresses. Okay, so in the following exercises we will only be dealing with the reference string itself, which is a list of all the page numbers that a process is accessing. And so the typical relationship between the number of frames and the number of page faults looks this way, right? So if we only have a few frames in the physical memory, then we're going to end up with a high rate of page faults, right? Because there's just a few of them and there's multiple pages that are competing against each other to be allocated those frames. However, if we have lots of frames, then the page fault rate decreases because now we have space to accommodate all those requests. And so the simplest page replacement algorithm, of course, will be FIFO, right? First in, first out. So it must be expert in FIFO by now, right? So really we replace the oldest page in the queue. So we keep a queue of the pages accessed by accessed by a process. And so so if we have 0, 1, 2, then the oldest will be the head of the queue and the newest will be the tail of the queue, right? And then this is old and this is new. So with FIFO, we're always going to replace the oldest one, okay? and we're always going to replace the head of the list, and whenever there is a new reference to a new page, then we insert it into the tail of the queue. And so given this reference string, and if we assume that we only have 3 frames in our memory, then FIFO will end up with 15 page faults. But how did we end up with 15? So let's do the count together. Okay, so with FIFO we said the idea is we replace the oldest in the queue. So we have our reference string here, and then we said we start with 3 frames in memory. So initially we're going to assume they're empty. So we're going to put our first page, which is 7, and this is 1 page fault because 7 was not there when we needed it, but no replacement needed yet. Again, after 7 we need page 0, another page fault, but no replacement needed since we still have place in our memory. And then 7, 0, and page 1, another page fault, but no replacement needed. Now we are calling page 2, but we don't have any empty space, so we're going to replace the oldest, which is 7. Okay, 2, 0, 1. Right, so this is done, this is done, this is done. Now we are referencing page 0, but it's already there in memory, so no page fault. Next, 3, it's not in memory, so we do need to do replacement. So this has just been replaced. The oldest in this case is 0. So 2, 3, 1. And now we need page 0. The oldest is 1. So 2, 3, 0. We need 4, so the oldest is 2. 4, 3, 0. We need 2, so the oldest is 3. Then we need 3. The oldest here it's 0, right? Then we need 0, so we go back and update this. 2, 3. The next oldest is 2, right? 3 is already there, 2 is already there. Now we need 1. So we said the oldest is 2, so we're going to replace 2. So 0, 1, 3. Then we need 2, so the oldest now is 3. 0, 1, 2. So the oldest now is 0. So we need 0, 0 is already there. We need 1 is already there. Now we need 7, so we're going to replace 0. 7, 1, 2. And then we need 0, so the next oldest is 1. So 7, 0, 2. And now we need 1. And so 7, 0, 1. So how many total of page faults? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 page faults if we were to use first in, first out algorithm. And so if we have a memory that has 3 frames and it already contains the pages 0, 1, and 2, right? 0, 1, 2. And 0 is the oldest, okay? Then if we have this reference string, when page 3 is referenced, the first in, first out will replace which page. So if we want to reference page 0 is already there. When we want to reference page 3, we have to replace the oldest, so page 3 will be replaced. Page 0 will be replaced, right? The total number of page faults for this reference string is what? So with 0 is already there, so no page faults. So 3 will give us the first page fault, right? And then if you want to reference page 0 is not there, so we will replace the oldest, which is in this case 1. Okay, so this is another page fault, and then when we want to access page 1, we have to replace the next oldest, which is 2. This is another page fault. So a total of 3 page faults in this case. And so the problem with FIFO is it suffers from something called the Biladi's anomaly. So we've seen before that with more frames, we're supposed to have less page faults, right? The problem with FIFO is this is not always the case. Sometimes, even if we increase the number of frames, we may end up with higher number of page faults, and that's a problem with first in first out page replacement algorithm. And so this is an exercise to demonstrate the Biladi's anomaly. So I'm giving you a page, a reference string here, and I'm asking you to apply FIFO with assuming only 3 frames in memory, and then apply it again, assuming that we've increased the number of frames from 3 to 4. So normally we want to expect less page faults, but you will see that with FIFO, you're going to end up with higher number of page faults. So I'm going to leave you to do this exercise on your own. So the next algorithm we will discuss is the optimal page replacement algorithm. So it is known to have really the lowest page fault rate, and it does not suffer from the Biladi's anomaly. And so the idea is to replace the pages that will not be used for the longest period of time in the future. So let's take the same reference string to understand this algorithm. So again, we're going to assume we only have 3 frames in memory. So the first page fault now for page 7, then again same thing for page 0, and then the third thing is for page 1, so 701. Then the next page reference is for 2, so it's not in memory, so we need to choose a victim. So our candidates are page 7, 0, and 1. So we will look ahead in the future in the reference string and compare when will each one of these pages be used. So we have 0 here, right? And then 1, the first reference to page 1 is here, and the first reference to page 7 is here. So the furthest away in the future is 7. So we will choose 7 as the victim. So 2, 0, 1. Right? So again, this is done, this is done. So now page 0 is already there in memory. Next, page 3. So we have to choose a victim, and the candidates are 2, 0, 1. So 0 is here, 2 is here, and 1 is the furthest in the future. So we will replace page 1. So 2, 0, 3. Okay. Next is page 0 is already there in memory. Next, page 4 is not there, and the victims are 2, 0, 3. So page 2 is here, 3 is here, and 0 here. So 0 is the furthest in the future, and we'll have to replace it. So 2, 4, 3. Next is page 2 is already in the memory. Next, page 3 is already in memory. Next is page 0. And so the victims are 2, 4, and 3. So 3 here, 2 here, and 4 won't be actually referenced in this reference string, so it's our victim. So 2, right, 0, and 3. Next, page 3 is in memory. Next is page 2, it's in memory. Next is page 1, and we have to choose a victim. And so 2, 0, 3, we have 2 here, 0 here, and 3 won't be referenced anytime soon. So we choose 3 to replace with page 1. Next is page 2 is already in memory, page 0 is already in memory, page 1 is already in memory, page 7 is not, and so we compare 2, 0, and 1. So 0 is here, 1 is here, but 2 is the furthest away, and so we replace it with page 7, right? Next is 0 is already in memory, and 1 is already in memory. So a total of 1, 2, 3, 4, 5, 6, 7, 8, 9 page faults with you if we're using the optimal algorithm, right? And this is the final view of memory after applying the optimal algorithm. And so if we have a memory that has just 2 page frames that already have pages 5 and 3, then the question is about when is the first page fault will happen. So we have reference to pages 5, 5, 5, which are already there in memory, and then the first page fault will happen when we reference page 1, which is not in memory. So which page will be replaced then? And so since we're doing the optimal algorithm and the victims are 5 and 3, we're going to look ahead in the future and see that we first go into reference page 3, then 5 further away, and so the victim will be page 5. And so this is another example to illustrate the result of the optimal page replacement algorithm. So we have page 1, reference to page 0, and we're going to assume we have 4 frames in memory. So the first is a page fault and the rest is still empty, right? And then reference to page 1. So 0, 1, 2 frames empty. And then reference to page 4. So 0, 1, 4. And then reference to page 0. So it's still in memory. So 0, 1, 4, 0 in memory. So we're not going to consider it. And then reference to page 2. So 0, 1, 4, and 2. And then reference to page 3. And so with the optimal, now we need to execute the optimal page replacement, and the candidates are mainly 0, 1, 4, and 2. So we're going to look ahead and see that we have 0 here, 1 here, and then 2 here, and 4 is the furthest away. So that's our victim, and the rest remains the same. And then a reference to page 0, it's still in memory. Reference to page 1 still there. To page 0 is there. Page 2 is there. Page 3 is there. Now page 4 is not there, and our victims are, our candidates are 0, 1, 3, and 2. So we have 2 and 1, so we have either 0 or 1. That will not be referenced anytime soon, so we can randomly pick 1 to replace. 3, 2. The next is 2 is already in memory, and 3 is already in memory. So the number of page faults here are 1, 2, 3, 4, 5, 6 total of page faults. And so the optimal algorithm, as we just saw, it yields the minimum amount of, or the minimum rate of page faults, and it doesn't suffer from the Biladi's anomaly. However, the main problem with the optimal algorithm, as we just saw, is it requires future knowledge of the reference string, right? So it is necessary for us to know which pages will be referenced in the futures. But we do not have this information. We don't know the future reference, the future pages that will be referenced in the future by that process. And so we need a different algorithm that does not necessarily needs knowledge of the future. and that's the least recently used algorithm. So instead of looking at the pages that will not be used soon in the future, we're going to look in the past and replace the pages that has not been used recently. Okay. So again, this is the same reference string, and we're trying to apply the least recently used algorithm. So again, we have 3 frames. Reference to 7 will cause the first page fault, and then reference to 0, and then reference to 1. Right? And now that we want to reference page 2, we're going to look in the past and pick the furthest away, which is page 7. Okay, so we will replace page 7, 1, and then reference to 0 does not yield a page fault because it's already there, and then page 3, and the victims are 2, 0, 1. So 0 is here, 2 is here, and 1 is the furthest. And so 2, 0, 3. And then 0 is already in memory. Now 4, and the victims are 2, 0, 3. So 0 here, 3 here, and 2 is here. So 2 is the victim. Right? And then reference to page 2, and I have to look at 4, 0, and 3. So 3 is the victim. 2, 0, 4. And again, reference to page 3. So 2, 4. So 0 is the victim in this case. 3, 2, 4. Again, another page fault by 0. So I have 3, 2, and 4 is the victim. It's the furthest away in the past. 3, 2. So 3 already in memory, 2 already in memory. Now number 1, and my victims are 2, 3, and 0. So 0 is the furthest away. Right? Next, 2 is in memory, 0 is not. So I'm looking at 2, 1, and 3 is the furthest away. 1, 2. Next, 1 is already in memory, but 7 is not. So I'm comparing 1, 0, and 2. So 2 is the oldest, or the furthest away in the past. 0 is already there, 1 is already there. So how many page faults? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this yields 12 page faults using least recently used algorithm. Right, all RU, compared to 15 page fault when we used FIFO. Okay. And so as we saw, the least recently used is better than FIFO. Okay, it gives us less page faults, but it is worse than the optimal algorithm, which only gave us 9 page faults. But as we saw, we cannot apply the optimal algorithm because we do not have knowledge of the future. And so if we have this reference string and we want to compare FIFO versus least recently used, and we only have 3 page faults, 3 frames, okay, 3. If we were to use FIFO, then first page fault for 0, second page fault for 1, and the third page fault for 2. Okay, so 0, 1, 2, and then 0 is already in memory, so we gotta use, and then we're gonna move to the page 3. The oldest here is 0, so we're gonna replace 0 by 3, and then the next reference is 0, and then next oldest is 1. So how many page faults? 1, 2, 3, 4, 5 page faults. Now if we are using least recently used, And so the first page fault is for 0, the second one is for 1, again the third one is for 2, and then 0 is already in memory. And then for 3, least recently used, the victims are 0, 1, and 2. We're gonna look in the past, 0, 2, 1. So the furthest away is 1, so I will replace page 1. Right, and then the next reference is to page 0, which is already there. So how many page faults? So 1, 2, 3, 4. So only 4 page faults for recently used versus 5 page fault for first in, first out. And so another exercise here to practice least recently used. So we have reference to, and we have 4 page fault. So the first page fault for page 0, and then for page 1, and then for page 4, and then 0, 1, 4. So this is done, this is done, this is done. 0 is already in memory, and then for page 2. And then we reference page 3, but it's not in memory. So we're going to compare 2, 0, 4, and 1. So the furthest is 1. So I will replace 1 by 3. And then 0 is already in memory. 1 it's not. So I have to compare 0, 3, 2, and 4. So 4 is the furthest away. Okay. Next reference to 0 is already in memory. Reference to page 2 is already in memory. Reference to page 3 already in memory. Now page 4. So I'm comparing 3 with 2, 0, and 1. So the furthest is 1. So that's where I'm going to replace. Next reference to page 2 is already in memory. 3 is already in memory. So total number of page faults is 1, 2, 3, 4, 5, 6, and 7. So total of 7 page faults. So when we did this exercise with the optimal algorithm, we ended up with only 6 page faults. And so least recently used, it's better performing than first in, first out, but it's a little slower, but it also needs special hardware support, right? So how can we know the order of references to those pages that were accessed by the process? So we may use the reference bit, so a bit that we set to 1 when a page is referenced, and initially it's 0 when it's not. But this will give us the information about whether or not it was referenced, but nothing about the actual order of references, so we can choose the oldest. Okay, and so there are multiple approximations to still do something that's similar to least recently used, and the one that we are going to learn about is called the second chance algorithm. And so the idea with the second chance algorithm is similar to FIFO, but we do incorporate the reference bit. And so the idea is when we want to replace a frame, then we check our frames first in, first out, and then the first one to be found that has a reference bit equal to 0, meaning it hasn't been referenced, then we immediately replace it. But if we don't find any, then what we do is we set all the frames that have a reference bit equal to 1, which means they were referenced, but what we do is in the first pass we're gonna set it to 0, okay, but we're not gonna replace it immediately. We're going to give it a second chance. And so we're gonna go ahead and check all our list of frames in a first in, first come order, and then we go back again in the second pass, and anything, the first page that has a reference bit equal to 0 will be replaced immediately. Okay, so it's like we're doing two passes. In the first pass, we're setting anything that has a reference bit to 1, we set it to 0, but we're not going to replace it immediately. We're going to give it a second chance. Only in the second pass that the first page that has found to have a reference bit equal to 0 will be replaced. And so let's apply the second chance algorithm to this example. And so assuming that we have 3 frames and they're currently holding pages 0, 1, 2, and 3, and this is the corresponding reference bit. Okay, so 0 meaning not reference, 1 means it's reference. So currently only page 1 is actually referenced. So this is our reference string, and so the first reference is to page 2, and so we look in our memory and we see that we already have page 2, but its reference bit is set to 0, and so we're going to change its reference bit to 1 because we just referenced it, right? But the rest remains the same. Okay, 1 1 0 0 3 0. And so next thing is a reference to page 1. So page 1 is already in memory and its reference bit is already set to 1, so nothing changes. So 0 0 1 1 2 1 and 3 0. Next, we reference page 4. So we see that page 4 is not in memory, so we have to choose a victim. And since we're using the second chance algorithm, so the idea is to start a pointer, so with FIFO, first in, first out, and we're going to check the reference bit. And the first page that has a reference bit set to 0 is going to be replaced. Let's see, the first page here is page 0 and its reference bit to 0, so this is easy. We don't need 2 passes. We already found a victim, and so we replace it to 4 and we set its reference bit to 1. The rest remains the same, 2 1 3 0, and we advance the pointer to the next page, right? So the pointer was here, now it's going to be moved here. The next reference is to page 0. It's not in memory yet, and so we have to apply the second chance algorithm, starting with where the pointer left off, which is page 1. So page 1 has reference bit to 1. We can give it a second chance, but we're going to set its reference bit to 0. Okay, so the first page remains the same. And so we advance our pointer here. Again, it has a reference bit set to 1, so we're going to give it a second chance, but set its reference bit to 0. Advance the pointer here. Page 3 has a reference bit set to 0, so this is a good victim that we're going to replace. So 0 1, and then we advance the pointer back here so that for the next reference bits we start our algorithm from this spot. And so this is another exercise for the second chance algorithm. And so we have 4 frames, assuming they're initially empty. And so we have reference to page 0. So we're going to put it in the first frame and we're going to set its reference bit to 1. Sorry, it has been referenced, so it's 1. Next is reference to page 1. So 0, 1, and then 1, 1. Next is reference to page 4. And so 0, 1, 1, 1, then 4, 1. Reference to page 0 is already in memory and the reference bit is already 1. So nothing changes. 0, 1, 1, 1, and 4, 1. Reference to page 2, we still have one more frame empty. So 0, 1, 1, 1, 4, 1, and 2, 1. Reference to page 3, it's not in memory, so we have to choose a victim. So we start our cursor here. We're going to set its reference bit to 0 and give it a second chance. Next, we advance the cursor here. We're going to set its reference bit to 0 and give it a second chance. Sorry, this is 1. Okay. Next, 4, we give it a second chance again. Next is 2, we're going to give it a second chance again. And the cursor is back to the first spot. And so that's our victim. So it's going to be replaced by 3. Okay, and we're going to set the reference bit to 1. Okay, so this is number 1. Next is a reference to page 0. It's not in memory, so the cursor has moved here after we replaced the first page, and so we check its reference bit. It's 0, so it's going to be replaced. So 3, 1, and then 0, 1, 4, 0, and 2, 0, and we move the cursor to the next one. And so reference to page 1 will replace page 4. And so 3, 1, 0, 1, 1, 1, and we move the cursor here. So it's still 2, 0. Then reference to page 0 is there, and its reference bit is 1, so nothing to change. Reference to page 2, it's there, but we have to change its reference bit to 1. And so 3, 1, 0, 1, 1, 1, 2, 1. But the cursor, remember, it's still here. Reference to page 3, it's there, and its reference bit is 1, so nothing to change. Now reference to page 4, it's not there, and so we have to choose a victim. And so the cursor is right here. Its reference bit to is set to 0, so we're gonna give it a second chance and set its reference bit to 0, and then we go up back again to 3. We're gonna set its reference bit to 0 and give it a second chance. Then the next, we're gonna set its reference bit to 0 and give it a second chance. Again, we're gonna set the reference bit of 1 to 0 and give it a second chance. Back to this last one, its reference bit is 0, so we will replace it by 4 and set its reference bit to 1, and then advance the cursor back to this spot. Next, page 2, and so since our cursor is here, reference bit is set to 0, so we're gonna replace it by page 2 and set the reference bit to 1. And so 0, 0, 1, 0, and 4, 1, and the cursor will advance to this spot. Reference to page 3 is not in memory, and so since the cursor is in this spot, that's what we're going to replace. So 2, 1, 3, 1, and then 1, 0, and 4, 1. That's the final state of the memory. So number of page fault, we have 1, 2, 3, 4, 5, 6, 7. Sorry, no, so not each one of these is a page fault. So we're only going to consider the ones where we did replacement, right? And so we did apply replacement here, 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 but we didn't do replacement here because 0 was already there. We did apply replacement here. I think we applied replacement here again with 0. We applied replacement here again, it wasn't there. Page number 1 we did replace, yes. Page number 0, I think it was already there. Page number 2 was already there. um, page 3 was already there, but page 4 was not, so we did replacement here. Page 2 was not, we did replacement here. Page 3 was not, we did replacement here. I think a total number of 10 page faults. The idea is whenever you apply a page fault, you can put like an asterisk here or a cross to remember the count at the end. Okay, I forgot to do that at each time we got a page fault. That's why I had to go back and do the count all the way in the beginning. So to avoid any miscounts, you can do that at the same time. So whenever you apply the replacement algorithm, you put like an asterisk or star or something to remember the count.